can very quickly answer the question before also. What some idea that people have had is actually to replace a face with a random face, and so hide that way, so that you actually have images with with faces in and not just blurred faces. Anyways, so I talk today also about spatial AI, and in particular how we can use this both to help humans get things done and also towards enabling robots to get things done. So, so essentially, first on the kind of understanding the 3D world around you if you want to get things done in a spatial, in a 3D world. So we live in a 3D world, so our context is 3D, and so it's often important to do that, not only the geometry, but also essentially the semantics of the world, so what's where in the world, and even a bit more than that, as we'll discuss. This is both towards devices like your phone, but also wearable devices. I've worked on this device at Microsoft, so I went to Microsoft to actually help develop elements too. But also applied for robotics and so on, and of course more and more towards humanoid robotics also. Here's a short video that will show you a little bit what we're envisioning in terms of enabling people to get stuff done, so to really support people.
This is work.
It's a light.
We're giving eyes and ears to AI. So the world becomes your prompt and your interface. This is work. Working. These are thoughts happening.
Hey, Copilot.
Plans populating.
Copilot, when was this last replaced?
Information gathering. Instructions guiding. Schematics aligning. People connecting. Problems solved.
Copilot?
Hey, Copilot. Copilot.
Okay, so you get the idea. Now, if you want to enable that, you can't just do it with a big multimodal vision language model or so that somehow has the answer to everything. First thing that people often forget is you actually need to know in which specific place you are, to know, for example, which specific machine is in front of you, what the maintenance history of that machine is, not just recognize the generic type of machine it is, and then have some generic instructions on what to do. You actually need the specifics. You need a memory of the world. You need to know, you need to build up essentially a memory and a representation of the particular world in which 3D representation in which you're working. First thing and then to be able to access that, to do spatial accessing of the data, you need to localize essentially. So as here, Avi was walking around in our offices and she's looking around, we actually have in a digital twin a representation of what she's seeing, and so the computer, the Copilot, essentially knows what she's looking at, and here you just see a visual representation. But of course, you would have all the underlying data related to IoT data, other, all of the relevant data that can be used to help solve tasks. Now, to do that, you would like to not have to, bring in, serving equipment and build up a very expensive digital twin and this and that. What you would like is to be able to do that just as a byproduct, keep generating an always up-to-date representation of the environment just by actually walking around in the environment with those devices. So while we use this to access and to provide an experience to the person, at the same time that data can move to the cloud. So this is a service that we've built at Microsoft, an experimental service in Azure. Every device kind of uploads its own data. In the cloud, we figure out when people walk in the same spaces and can merge that into a single, combined representation of the environment. This can be people, this can also be robots, as you saw. There's multiple layers of representation in there. We're here to show you this working at scale. This was just with a single device walking around in a building for a few hours. This is Studio C on the Microsoft campus. I just walked around for a few hours, zigzag around. You see the trajectories there, and then you see all the surfaces, the whole building essentially was represented. These are still things that are way beyond a lot of the deep learning based, methods like VGGT or other methods that take a few images and will reconstruct a single local place. Here we're talking about many, many, many different local spaces, all in one consistent representation. So here's this at the, let's say, industrial scale of a factory, very complicated structure. Here also just different people walking around with devices, all of this automatically merged into a single kind of consistent map of the whole representation. And then as people do maintenance, other things, so they just walk around there, they're always localized. As they do maintenance somewhere, that data can automatically be recorded and then essentially included in the representation. Okay, so now let's take a step back in history. So this was almost 30 years ago, where to show that we could already do a lot of these 3D geometry reconstructions. As you saw here from this input video, we first figure out where keyframes were located with respect to the scene, reconstructed a sparse representation of the scene, and then as you see on the right, a dense representation of the scene. This was at a quality that still essentially today's novel methods actually don't surpass the quality of these models. Now, what's changed is we can do that at a bigger scale, we can do it faster, and the big challenge in all of these things was finding corresponding points between images. That's something that now works a lot better. And so instead of needing a careful video sequence, on an object that was easy to track correspondences, we can now work in much more generic context. This is ProMap that Ivan mentioned. So this is a tool that a lot of people use, and that essentially from a photo collection will kind of figure out which images kind of look at the same thing as other images. From building up a graph of all the images that relate to each other, then through geometric computations computes first a sparse representation, the number of key points, as well as the position of the cameras, the things in red.